Hi guys, this is Xing and I'm glad to talk about our work today, ProS, Facial Omni-Representation Learning via Prototype-based Self-Distillation. And before I talk into the work, I want to thanks to my colleague, Yiyu Zheng from Prototype Labs, and I also want to thanks to Professor Xiaoming Liu from Michigan State University, and also thanks to the Professor Yu Cheng from the Chinese University of Hong Kong. And in this work, we present a novel approach called Prototype-based Self-Distillation, abbreviated as ProS, for unsupervised face representation learning. As we know, the existing supervised methods heavily rely on a large amount of annotated data, which poses challenges in terms of the data collection and privacy concern. To address these issues, we proposed the ProS, which leverage a vast collection of unlabeled face images to learn the comprehensive facial representation. In particular, ProS learns the facial representation via a vision transformer architecture. And after pre-training, the learned model serves as a backbone for downstream tasks, including facial attribute estimation, facial expression recognition, or landmark alignment. And in this work, extensive experiments demonstrate that our method achieves state-of-the-art performance on various tasks, both in full and few-shot setting. In particular, ProS is trained in the self-knowledge distillation via a local to global manner, and our work is inspired by Dino, as shown on the right, but with two different changes. The first one is we propose a modified sample to prototype matching loss, and the second one is we proposed a facial-aware retrieval system to obtain curated data. And these two modifications are highlighted in red in the left figure. And as we shown in left, the global and local images are obtained from the same input images via multi-crop, followed by the proposed face-aware retrieval system. And the face-aware retrieval system aims to filter out most non-face images. And after that, the curated images are fed into the two sets of augmentations. And the augmented images in global and local views are given to the teacher and the student models separately. By matching the features extracted from the teacher and student model, the loss gradient is backpropagated to the student model only for updating parameters, while the parameters of the teacher models are updated through the exponential moving average. And the motivation behind the face-aware retrieval system is that during training we observe there are certain amount of non-face images obtained in the local view, as highlighted in the red bounding box in the left figure. And recent studies show those unidentifiable images are detrimental to the training procedure. And to eliminate those outliers, we built this retrieval system. And in particular, we compute the face embedding using the pre-trained arc-face model for both the global and local images, and the cosine similarity between these images are used as a distance measure. And we displace those local face images with similarity lower than a threshold. And we demonstrate two curated image samples in the left figure, as shown in figure 3. And in addition, to boost the feature discrimination, we introduce a set of learnable prototypes during training. Instead of directly computing the similarity between the features extract from the teacher and student models, we compute two sample to prototype distributions, one between the teacher samples to the prototype, and the other one between the student samples to the prototype. And we use the differences between these two distributions to penalize the model training. In this manner, both the prototype, the teacher, and student models are optimized in each iteration, where the features try to get closer to positive prototype and keep away from negative prototypes. And in this table, we evaluate our proposed method ProS with other pre-training models, for example, the MAE, and Dino, and MSN. And based on the result, we can observe that ProS outperforms other baseline models with pre-training on a larger face dataset. In addition, we also show a proposed method on several face-specific downstream tasks. For example, in Table 2, we evaluate the proposed method on syllabi and AFWA dataset with face attribute estimation task. And as we can see that in the future setting, our proposed method achieve a reasonable comparable result with other baseline models. However, in the future setting, our proposed model achieve a new state-of-the-art result when compared with other supervised method or unsupervised method. In addition, we also evaluate the proposed model on two more tasks. One is a facial expression recognition task on AffectNet 8 and IFDB dataset, as shown in the figures, as shown in the tables 3. And we also evaluate on the facial alignment task in table 4 in terms of the WFLW and 300W dataset. And as we can see on the facial expression recognition test, our model achieved an even better result compared with the supervised method EAC. And we also achieved excellent performance on the future setting. And on the facial alignment test, our proposed method also achieved a reasonable or comparable result when compared with other supervised or unsupervised model. And finally, we do two more visual analyses on the proposed method. The first one is testing visualization on the node prototype and by finding the nearest neighbor in the training data. And in particular, we can see that when trained the model with more data, more image data, we can find the node prototype features are more sparse, and it's kind of give a more better coverage on the node space when compared with the features learned on fewer image data, as shown on the left. And also we do the visual analysis of the attention heat maps on the node feature from both pre-training and fine-tuning the model. And as we can see in this figure, the node feature representation from pre-training model are more general than the ones from the fine-tuned model. That makes sense because of the feature on the fine-tuned model are more task specific. And that's it. Thanks for watching. And for more detail about this work can be found in the paper and also the supplementary documents.